Hey folks, and welcome to another one of the Fermi Physics Solutions concept videos. This set of videos is going to look at electric circuits and understanding the behavior of electric current. So what I'm going to do to first explain how electric current behaves, I'm going to look at a simple scenario that you're probably all familiar with. Imagine you have a little tennis ball on the end of a string and that's held a couple of meters just above the ground, and ask yourself, well, what's going to happen to that ball when you cut the string? So we cut the string, we see the ball falls down towards the earth, and we know that that's being pulled down by gravity. So gravity pulls the ball from a high area down to a low area in terms of height. And in this case, we can see it's going to fall all the way down until it hits the surface of the ground. So if I want to think about this in terms of energy, I can say at the top the ball has high potential energy, and at the bottom, where it's just about to hit the ground, it's going to have low potential energy. And once I cut the string, then the gravitational force is going to pull the ball down, and it's going to move from an area of high potential energy to an area of low potential energy. And we can see that again when we cut the string and the ball falls. And again, it will keep falling to the lowest potential energy that it can get to until it hits a surface like the ground, in which case it's going to stop. Now, keep that idea in your head, and now what I want you to imagine is two positively charged plates. So here we have not two positively charged plates, a positive and a negatively charged plate. And between those plates, we have the ball again. So just imagine a little tiny hole that's been drilled through the top plate. We feed a string through it, and we have a little ball there, and that has a charge of, just let's make it really simple. There's exactly 1 coulomb of charge on that little ball. So again, just ask yourself, from your understanding of forces in terms of electrostatics, what is going to happen to that ball when you cut that string? And as we can see, the ball moves from the positive plate down towards the negative plate. And again, you can think about this in terms of forces. So you can say that the positive plate repelled the positively charged ball, and at the exact same time, the negative plate attracted the positively charged ball. So here we can see the electrostatic force is causing the movement when you remove that string. Again, if I want, I can think of this in terms of electrical potential. So we would say that you have high electrical potential energy when you're closer to the positive plate, and you have low electrical potential energy when you're closer to the negative plate. By the way, it doesn't matter what orientation you have. If I were to put the positive plate on the bottom and the negative plate up towards the top, I would still have high electrical potential energy at the positive plate, and I would still have low electrical potential energy at the negative plate. So while gravity, it does matter which way is up, down, left, and right to give you your potential energy. The potential energy in this case doesn't matter about orientation, just matters about whether you're closer to or further away from the positive and negative plates. So again, cut that string, and I can see my positively charged ball moves from a high potential to a low potential. Okay. So one thing I notice here is that electric charges pretty much behave the exact same way as any normal mass does under the force of gravity. So they can move from high electrical potentials to low electrical potentials the same way gravity causes masses to move from high potential energy to low potential energy. So again, I put the strings, and they both move pretty much the exact same way. It's just different forces acting on different types of bodies here. So what I can then think about it is, well, I have a high potential energy at the top and I have a low potential energy at the bottom. That means there's a difference in the potential energy when you move that charge from the top plate to the bottom plate. And we would call that the potential difference, which used to be called the voltage, when we're talking about the energy difference of moving exactly 1 coulomb of a charged body. So if I take this object here and I give it the standard unit of charge, which is 1 coulomb, then the difference in potential energy that it gets from here to here is what we call the potential difference, or in other words, the voltage. It's the difference in energy that happens. So it's the difference in energy that happens when the ball moves from the high potential to the low potential when it has a charge of 1 coulomb. So again, we also know that we also know that electric currents, they don't look like what they look like on the left. In fact, probably a more common version is what's on the right hand side there. So while the idea that we need to have in our head to understand it is that the object moves from a high to low potential, and the easiest way to show you that is to show you that sort of picture there. That's still got the connotations of gravity in the back of our head, so we're going to try and look at what this would really look like. Again, the positively charged ball has to move from a high potential to a low potential, so it has to move from the positive to negative. And what that will end up doing is actually doing this. Now, the only other thing that it will do is it will go through the battery due to a bit of electrochemistry. Now, that's not necessarily on the course that we need to understand right now. But as you can see on the right hand side, the positively charged ball is falling from a positively charged area to a negatively charged area, or a high potential to a low potential. It's just doing it along the electrical wire. Again, what happens on the inside is really a bit of electrochemistry, and that's a slightly different occurrence, which I'll address in a simple manner later, but the actual chemistry involved I will not. Some people think it's the charge from the battery that moves around. It's actually every charge everywhere in the circuit that moves around. So a more accurate way to represent it, and I'm only going to use 6 charges. Realistically, there's millions, billions, or even trillions of charges moving around. What it really looks like is more this. So as you can see, you have every charge at every point in the wire moves around in the counterclockwise motion. And again, it's moving from the high potential down toward the low potential until it goes into the negative terminal of the battery, in which case it's going to go back up. Now, I like to think of this, even though it's the wrong term to use, but I like to think of this, that all those charges are falling from the positive to the negative, or they're falling from the high potential to the low potential. Falling is the wrong word to use, but I actually think it kind of explains it quite nicely as well. What happens inside the battery is, like I said, is electrochemistry, but this is a nice little model to think about it anyway. So if you imagine kind of like a travelator on the inside, and the travelator, what it does is basically 2 rotating axles with with kind of a rolling surface going between them. You probably see these things at the airports when you're in a rush to get down to your terminal. It's like an escalator that's flat and moves horizontally along the ground. And what that does is that takes the charge from the negative terminal and it moves it up towards the positive terminal. Now, obviously in real life, there's metals and acids reacting together to cause this, but as a simple model to understand it, the charges are moving internally from the negative up towards the positive, and they gain their potential energy as they do this, again because, like I said, the inside model, which looks like a travelator, brings all those charges from the negative terminal over towards the positive terminal. Once they get out of the battery and they're back onto the electric circuit, they can, again, and I'm going to use this in inverted commas, they can fall from the positive high potential down to the negative low potential. And that will keep going as long as you have enough acid metal reactions happening inside your battery to keep this process going. Because once those chemical reactions cease, then again, inverted commas, the travelator will stop moving your charges internal from the battery, and then your battery is essentially spent and you can't use it again. So I hope that made the idea of how charges work clear. Some of the next videos are going to look at how the behavior of current moves through a circuit itself.